So the goal that we've been working towards is the ability to determine the rate of heat transfer from a heated flat plate into a fluid stream that is passing over it. The analysis that we've done has depended upon understanding the boundary layer that forms on the flat plate and the similarity analysis that is coupled with the boundary layer analysis that we looked at gives rise to this dimensionless parameter that we have referred to as the Nusselt number. So the Nusselt number is this dimensionless parameter, and it's related to the actual quantity of interest that we're looking for, the convection coefficient H, where the Nusselt number is defined as the convection coefficient times the length scale of interest divided by the thermal conductivity of the fluid. So if we can determine the Nusselt number, we can then obtain from the Nusselt number and knowledge of both the fluid properties, in this case the thermal conductivity of the fluid, and the length scale that we're working with, we can then get the convection coefficient. And then once we have the convection coefficient, we can utilize Newton's law of cooling to obtain the total rate of heat transfer from the plate itself. So let's take a look at what we're trying to do here. So we have different situations. The first one we're going to look at is what we're referring to as the local laminar correlation. So we would use this if we are at a location on a plate that is somewhere between the leading edge and the location of transition from laminar to turbulent. So if we are interested in the amount of heat transfer from a relatively small region of the plate, say we'll use the term delta X to define a relatively small length region with respect to the total length of the plate, or in this case, the length of the plate from the leading edge to X critical. Then if we can determine the local heat transfer coefficient, we can then determine the amount of heat that is leaving this localized portion of the plate. So we will do that using this analytically derived version of the Nusselt number. So Nu sub x, so this is a Nusselt number that varies depending upon what x location you happen to be at. It's 0.332 times the square root of the Reynolds number times the Prandtl number raised to the 1/3. So in this case, we're using the local Reynolds number, where this x is the location of on the plate that we are interested in. And since we're using a laminar correlation, we are requiring that this x location be less than x critical. So then once we've verified this and determined or calculated the Reynolds number, in this case we would have to get this fluid property based upon the film temperature and the Prandtl number based upon the film temperature. We can then calculate the Nusselt number, and then once we have the Nusselt number, we again would multiply it by K, a fluid property that is also based upon the film temperature, divided by X. So this is the location of interest. That would give us a local heat transfer coefficient, and from that we can then get the heat transfer. In this case, I'm going to multiply H sub x by the area, in this case delta x times the width of the plate. So the width of the plate, if we didn't know the width of the plate, it would be per unit width. So in the unit of Q, if we know both of these parameters, Q will be given in units of watts. If we didn't know what the overall width of the plate was, the units of this would be watts per meter. And this all gets multiplied by the temperature differential. All right, so that's if we're on this side of X critical. We can also define a local turbulent correlation if this region of interest is downstream of the X critical location. So everything looks much the same here. I'm just calling this X2 to differentiate it with regards to the figure. And if we now look at the local Nusselt number, the turbulent correlation, so we again have an expression for the Nusselt number that is dependent upon the parameter x. In this case, the Reynolds number is now raised to the 4/5. Prandtl number remains being raised to the 1/3. The Reynolds number hasn't changed, but in this case, we are requiring that the X location be greater than X critical. And then, as before, we can calculate the local heat transfer coefficient and then determine the total amount of heat transfer in terms of watts from this localized region of the plated. So sometimes what we're more interested in is the total rate of heat transfer from some region of the plate. So we can have a region of the plate. Typically, we're defining this region as starting at the leading edge and then going up to some value, in this case L. Now, it is very typical that we would be interested in the rate of heat transfer from the entire laminar portion of the plate. And in this case, this length L would extend all the way up to X critical. So L would be equal to X critical. But it doesn't need to be. Sometimes we might be interested in the amount of heat transfer from the first third of the plate for some reason. So the total heat coming from this laminar correlation is going to be equal to the average heat transfer coefficient, again determined in the laminar regime. So these are given here. So we have the Nusselt number. Again, the textbook will write this as Nusselt number average with the bar over it, sub x, but I'm just explicitly saying x is equal to some distance L. We're just trying to clarify that it is a distance L that encompasses this entire region of the plate. And same thing for the Reynolds number. So now it's 0.664 times the square root of the Reynolds number times Prandtl number to the 1/3. We have the same expression for the Reynolds number here, except I'm using L to, and what we're really trying to define using L instead of X is to define that this is an average value where L is encompassing the entire length of the plate of interest. So when I say the entire length of plate, I mean this region that we've defined. And in this case, since we are laminar, L must be less than X critical. And then, as before, I just keep writing it here, we have the average heat transfer coefficient is obtained by using the average Nusselt number multiplied by K divided by L. And then we can get the rate of heat transfer from that region of the plate by multiplying the average heat transfer coefficient by the total area, length times the width of the plate, and the temperature differential. Now, the next thing we might want to look at is a situation where we're still looking for an average rate of heat transfer from the leading edge up to some distance that is past the X critical location. So this is referred to as an average mix correlation because the area of interest includes both laminar and turbulent areas of the plate. So we now look at the average Nusselt number for a mixed correlation. So what we have now is a slightly different variation because we have this average Nusselt number that is 0.037 times the Reynolds number raised to the 4/5, but now minus a term here, A, and times Prandtl number to the 1/3. So in this case, the Reynolds number has to be greater. So the Reynolds number at this length L. So I'm remember the Reynolds number is a linear function. So when I calculate the Reynolds number at this location, X equaling L, it has to be greater than X critical, and it's also required for this correlation to be less than 10 to the 8th. So this A is a parameter that is based upon whatever value we're using for the critical Reynolds number. So again, I will reiterate that while it is very common for this value to be 5 times 10 to the 5th, there are many problems or many instances where you are told a different critical Reynolds number. And once you've determined this parameter A, you plug that back in here, you get the average Nusselt number for the mixed correlation, and you can again get the average heat transfer coefficient and use that to get the total rate of heat transfer from the plate. Now, the last one that you might want to take a look at is what would happen if you wanted to actually know for the rate of heat transfer from a portion of the plate that is completely turbulent. Well, there is no specific correlation for this. You can use the correlation for the mixed condition and utilize that to obtain the average or the rate of heat transfer from the leading edge up to this point L. And then you can then calculate what the heat transfer rate would be for the entire laminar region of the plate, and you can subtract the two of them. So instead of actually getting a correlation for the Nusselt number, you're actually just utilizing the values of the heat rate for the mixed condition and the heat rate for the laminar condition, and utilizing the two of them to get the heat rate from a specified region of the turbulent region over the plate. And I'm expressing that here, so the average heat transfer from a turbulent region of an isothermal flat plate is obtained by subtraction. So we have to be in a region where where X is greater than X critical and less than L, or that is the region that we're in. And we would determine the rate of heat transfer from the laminar region of the plate, so from 0 up to X critical. And we would determine the average rate of heat transfer from the mixed portion from 0 to L, and then subtract the two.